Module 14, Chemical Kinetics by Audrey Berry. So an overview of Module 14, Kinetics, and what I will be discussing with in this presentation. So we're going to define what is chemical kinetics and the history behind it, the effects of both concentration and temperature, understanding the basics of concentration and temperature, problem questions regarding both of these, and real-life examples of how concentration and temperature affects rates of reactions. What is chemical kinetics? Kinetics is the study of the rate of chemical reactions, specifically at what speed they occur. It also involves the investigation into components that affect these reactions. These factors are concentration, temperature, pressure. Chemical kinetics history. Ludwig Wilhelm was the father of chemical kinetics, and he discovered the rate and speed of the reaction is dependent on the reactants available. He was the first to study the rate of inversion, which explains chemical processes and enzymatic activity that happens in our body. How does concentration affect the rate of reaction? So as the particle theory states, when we increase the concentration, collisions happen more frequently, and by increasing the concentration, this allows for a higher frequency of opportunities for particles to react with one another. How does temperature affect the rate of reaction? So temperature plays a large role when it comes to these reactions. So an increase of temperature will increase the movement of the particles and allow a higher affinity for collision, and decreasing the temperature will decrease the movement of the particles, creating a lower affinity for collisions. Basic concentration kinetics. So here we have a basic understanding by using letters. So we have reactant A and product B. So to define the rate, we would use the negative change in the reactant over the entire time. And for products, we would have a positive sign, and it's the change in the concentration of the product over time. Basic temperature kinetics. So we use this equation called the Arrhenius equation, and it's K is equal to AE to the power of EA over RT. K is the rate constant, EA is the activation energy, T is temperature, R is the ideal gas constant, and A is the frequency of collisions, preferred orientation. So our first example, you're given the chemical reaction 2R plus 2E will give you 3P plus O, and express the equation for the average rate using concentration and time. So for the first reactants, we need to make sure to put a negative sign out front, and we also have to take into account the coefficients that are out front of it. So because this is a 2, our coefficient will be a half. And then for 2E, it will also be a half. And then for 3P, it will be 1/3, but it will be positive this time because it's a product. And for O, it'll be the delta change in 1 because there is no coefficient out front of it, so we assume that it's 1. The final rate will be equal to all 4 of these small equations that are equal to one another. For the second example, we're going to find the average rate of NO2 gas in the following equation. NH4 plus NO2 will give you N2 gas plus H2O. So to start, we're going to look at the changes of concentration from the final and the beginning, and we're going to subtract those. And then we're going to look at the time, which is the final time minus the first one. And we'll get negative 1.47 times 10 to the negative 7 mole divided by liter per second. When discussing rates of reactions, it's important to take into consideration the rate laws. So consider this equation below. AA plus BB plus so on will give you CC plus DD. The rate equation for the forward reaction is defined as rate is equal to the constant K over the change in A to the power of X times the change in B over to the exponent Y. K is defined as the reaction constant, A and B are the changes in concentration, and X and Y are the exponents defined by reaction orders. X is with respect to A, and Y is with respect to B. So here we have the rate law table, which will give you the overall reaction, the definition of the rate law, the units for the constant K, and a couple extras, the integrated rate laws and the half-life. So what's really important here is to understand that there's the zero order, the first order, and the second order. And the coefficients that are in front of these reactions are dependent on the rate law equations and the order that they are placed in. The units also depend a lot on the rate laws and which order is used. Here's a reaction order example. So given the chart below, we are going to determine the order for the experiment for the reaction of HNO3 plus H2O will give you H3O and NO3. So looking at the chart, it's clear during the first and second experiment, the concentration of HNO3 is doubled and the rate is quadrupled. This means that the second order with respect to HNO3. Next, we compare the first and the third experiment, and the concentration is doubled and the rate law has also doubled. So this is first order with respect to H2O. Next, we are going to determine the rate law equation and solve for the reaction constant K. So we're going to use the same equation as we used in the first problem, and using our knowledge from the table, we can conclude that reaction order for the equation is equal to the rate equals K, the change in the concentration of HNO3 squared, and the change in concentration of H2O. Now to determine the reaction constant K, we can sub in the values from the experiment in the table above. So rate is equal to K HNO3 squared times the change in concentration in H2O. So we get 0.04 divided by 0.250 times 0.200. And finally, for the K constant, we get 0.8. For the final equation for this rate reaction, it would be rate is equal to 0.8 times HNO3 squared times H2O. Now using a temperature example. So here below we are given reaction 1 and reaction 2. We're going to predict which reaction will have a larger K value based off our knowledge on temperature and rate of reactions. We're going to set up equations for both of them by plugging in the necessary values and solve these equations for the final K values. So for the first problem question, we'd predict that reaction 2 will have a larger K value because it has an increase in temperature. For the second question, we're given the formula, the Arrhenius formula. K is equal to AE to the power of negative EA divided by RT. So we're going to sub in the values that were given and making sure to multiply our kilojoules by 1,000 to give us joules. And then following that, the third question, we calculate the K value by subbing in all the values, and we get for the first reaction 0.000002, and for the second one we get 0.00011. So our prediction was correct. Reaction 2 does have a larger K value, and that's because of the increase in temperature. Concentrations affect on rates of reaction in real life. So here we have two examples. Tums, for example, 2 antacids tablets will neutralize the amount of stomach acid faster than 1 tablet will, and also we have higher concentrations of acid in rain erode marble, such as the statue of George Washington to the left here, faster than with lower concentration. And temperatures affect on rates of reaction in real life. We have temperatures that greatly influence our processes in our bodies every day, Enzymatic activities in our stomach are dependent on our internal temperature in order to function properly. And also, something as simple as baking bread, it rises in warmer temperatures compared to in colder temperatures. This concludes my presentation. Thank you so much for watching.